Oh, it's recording? Okay, okay. We gotta get back to normal. Alright, so this is part 2. Are you ready? So, I'm gonna back up just a bit, just in case you stumbled on this video by accident. You kinda wanna know the context. So basically, I'm transliterating an old rare book on a forgotten technology that you probably never heard of, and if you have, you're grateful to learn some more. And forgive my presentation skills, they're not the most pleasant in the world, but we can get by. So this is going to be a long video. The last one was about an hour and a half, so you might as well get comfortable or download an MP3 of this or something like that, and we'll get started. So where we left off is a little awkward, so I'm just going to back up a bit and get going. Once again, this is the Edison storage batteries monograph, um, and we'll continue as before. I had to get a good night's rest, so hopefully I'll be able to speak a little clearly, etc., etc. Okay, so what I'll do is I'll read text, but if there's diagrams and photos, I'll read the captions if there's any and show them to the camera, and then I'll read the bulk text. I plan to scan this into a digital format and put it on my eBay store, so that way you're able to access it raw instead of through me and my sort of leisurely read through. Okay, so section 2. I've already messed up. It's section 3. Section 3. In science and engineering, laboratory use. The nickel-iron alkaline type of storage battery is widely used in school and college laboratories, both 1. In science departments as a DC supply for instruction in electricity, magnetism, and physical chemistry, and 2. In engineering departments for demonstration of the principles and methods employed in the practical uses of storage battery power in industry. As a laboratory DC source, this type of battery has the advantages of long life, low annual cost, and dependability, which are the principal reasons for its wide usage in industry. More specifically, its ability to stand idle without deterioration when in a discharged condition is a great convenience, eliminating as it does the need of periodic charging or other attention required by the lead-acid type of battery during vacation periods. Its lightweight and durable steel cell construction are useful features in portable batteries, while its ability to withstand overcharging permits tapping a variable number of cells in order to obtain variable voltages as required without risk of injury. During subsequent charging, the cells that have been discharged the least must withstand a certain amount of overcharging in the course of bringing the others to a fully charged condition, but this does not cause damage to the nickel-iron alkaline type of cell. For use in science departments in which the function of the battery is solely that of furnishing a DC supply for the conduct of experiments, there are 2 ways in which the cells may be installed. A single battery, frequently of 100 cells or more, is connected through a switchboard and wiring system to the laboratory benches, thus making available a wide range of voltages. The other method is to use portable sets, generator sets. Each method has advantages of its own, and in large laboratories both are often used. Generally, however, portable sets have proved more satisfactory. In the use of a single central battery, You should try this someday if you think it's easy. Or you should give me some tips if you know how to do it better. And give me some pointers. Maybe I need a teleprompter. In the use of a single central battery, the large amount of secondary wiring necessary to distribute the current I think I'm just going to start over here, okay? Here we go. Each method has advantages of its own, and in large laboratories, both are often used. Maybe I'm going too fast, I'll slow down. Generally, however, portable sets have proved more satisfactory. In the use of a single central battery, the large amount of secondary wiring necessary to distribute the current that's it, I'm going too fast. In the use of a single central battery, the large amount of secondary wiring necessary to distribute the current from a common switchboard usually increases the investment unnecessarily without adequate compensatory saving of time or money in other respects. A complete discussion of the installation of a DC supply for the Science Department laboratory battery is beyond the scope of this monograph. This company's sales engineers, however, are at all times available for consultation on request to any of its branch offices or to the home office. Not at all times, they're long gone. Not in our time. Likewise, a list of science experiments employing electric current is considered beyond the scope of this booklet, as it is believed that the science instructor will prefer to formulate his own or to use those prepared by recognized authorities. On the other hand, the available authoritative literature relating to laboratory instruction in battery characteristics and their significance in practical industrial battery operation is much more limited. It is believed, therefore, that this is a subject on which a discussion will be welcomed by both instructors and students in engineering colleges. Instruction in the subject, while probably of greatest value to those pursuing courses in electrical engineering, is of value also in mining and mechanical engineering, since storage battery power is used extensively in mine haulage as well as in the transportation and material handling system of the industrial plant. Those expecting to enter marine architecture will also benefit since storage battery power is used on shipboard as a standby source for lights, hydraulic, steering engines. Ran out of tongue. We'll try this over. Well, I'm getting better. Maybe if I do this more, I can do a better job. But who has time for that? I had to take time, some paid leave to even ponder trying to attempt this. But what I do here will be up on the net for people to access at their leisure for many years to come. So maybe this is a good use of my time. Maybe what's a good way to say it? Maybe, baby. All right. Instruction in this subject, while probably of greatest value to those pursuing courses in electrical engineering, is of value also in mining and mechanical engineering, since storage battery power is used extensively in mine haulage as well as in the transportation and material handling system of the industrial plant. You gotta take a breath between sentences. I think that's another trick. Those expecting to enter marine architecture will also benefit, since storage battery power is used on shipboard as a standby source for lights, hydraulic, steering engines, and other purposes. A study of the industrial uses of storage batteries, as given in Section 1, will also be useful in indicating the various fields of engineering into which their application and operation extend. An excellent form of instruction consists in assigning the maintenance of laboratory batteries to the students. In this way, they will learn many details of the care of batteries in commercial use, with the possible exception of neglecting to flush and allowing the electrolyte level to fall below the plate tops. It is virtually impossible for the beginner to do anything that will cause permanent injury to the nickel iron alkaline type of cell. That's good news for me. Totally. I'm not saying I'm uh, perfect. You know, I'm mistake prone. I make all kinds of mistakes. Sometimes it's the best way to learn, but when you have a limited supply of antique batteries, you don't want to be taking too many risks, that's for sure. The following experiments and exercises have been selected to demonstrate to the student some of the more advantageous characteristics of the nickel iron alkaline type of storage battery. These advantages contribute in no small measure to its wide commercial acceptance. Exercise 1. Physical characteristics. Strength. The structural parts of the cell which must withstand the mechanical shocks and stresses incidental to practical use are mainly the cell containers, the pole pieces, and the grids which support the active materials. In the lead-acid type of cell, containers are generally made of hard rubber or other molded acid-resisting material, and the pole pieces and grids of lead. And then there's an asterisk, and I'll read what it's referring to right now. Asterisk says, an alloy of lead and antimony is also employed. I currently have some Group 29 batteries, and I believe they're a lead antimony combination intended for deep cycle marine or RV use. So that's today, and I'd say as a commentary that most lead acid types of cells now that you find have plastic cases or containers, which didn't exist back in their current form back in 1940 or before. In the nickel iron alkaline type of cell, containers, pole pieces, and grids are all of steel. From a mechanical engineer's handbook or other suitable reference source, obtain the tensile strength in pounds per square inch of hard rubber and lead. Then look up and compare with the tensile strength of steel. So this is these are activities to win over the loyalty to this nickel iron alkaline battery technology. It's basically, here, look this up, look that up, and train yourself, educate yourself why we say what we say. So these are pretty cool activities. I mean, if you got the time, that'd be something you want to do, educate yourself. I unfortunately haven't done it yet, and so I can't provide you the answers along with these questions, and they're not in here. Exercise 2. Physical characteristics. Active material retention. The finally limiting factor in the life of any storage battery is the length of time it is possible to retain the active materials in physical and electrical contact with the grids. In lead-acid batteries, the materials used for the purpose generally consist of wood, cedar, hard rubber, or spun glass. In nickel-iron alkaline batteries, the material used is steel. Compare the tensile strength of these materials. Exercise 3. Physical characteristics. Weight. That's weight as in gravity, influence, weight. Not weight as in weight on me to pull words out of my mouth that are not legible but understandable. Hearable. Is hearable the auditory equivalent of legible? Okay, so exercise 3, physical characteristics. Weight. So I should just say weight. Using the values of tensile strength obtained in the course of exercise 1, compute the thickness of a sheet of lead required to obtain the same tensile strength as that of a sheet of steel, 0.037 inches thick, as used in the grids of Edison nickel iron alkaline cells. Then look up the specific weights of the two materials. It will be apparent that steel permits greater strength in proportion to its weight than lead. Compare the weights of typical industrial truck batteries of comparable capacity as tabulated below. Calculate the percentage by which the lead acid batteries exceed the nickel iron alkaline batteries in weight. So there's a table here. I'll flash it up here in a second. It's called typical industrial truck batteries. Ooh, I'm getting better at reversing my... Okay. Seen that? You know, that was annoying. On another YouTube video, the gal kept asking, "Hey, do you see that?" And she was talking about steam in a greenhouse. And she would just say, "Oh, do you see that?" And it was annoying because it's as if, like, I can ask you any question in the world, and it doesn't matter what you say, I can't hear your response. This was pre-recorded. But it triggers something in people when they're intently learning through a medium such as this, and then a question is asked that would typically require like a response, like, "Do you see the steam?" or "Do you see that? Do you see that? Do you see the table?" And then the person is like, kind of, yeah, oh, yeah, move it this way, move that." But, you know, can't do that. It's pre-recorded. So hopefully you understand what I'm trying to say. Do you see that? As in, if you see that, awesome. But I can't fix it at this point in time. I only hope that you got what you needed. Okay, so I'll continue. And you remember, you can pause the video, and you don't have to be like the fastest reader in the world. You can pause the video and go through the scenes you need or the text you need, like that. The commercial value of the light weight of the nickel iron alkaline battery is that less power is required to haul it, whether on railway passenger cars, where the savings appears at the locomotive drawbar, or in industrial trucks where more... Yeah, I just think getting a good night's rest would improve my vocal gymnastics, but we'll continue. Let me restart. Only got a little bit more comparing to yesterday. Okay. I need to just get focused and narrate, right? Okay. The commercial value of the light weight of the nickel iron alkaline battery is that less power is required to haul it, whether on railway track. I think the way my eyes and my mouth coordinate, my eyes anticipate and my mouth estimates, and the way I read is most words are followed by other words commonly, and you start getting word strings, and then you just assume that they're going to string in a normal fashion. This is written in a little, using words I'm not familiar with. Using technology is probably not in vogue today. And as a layman on this stuff, it's messing up my word strings, right? So I need to slow down and get back on the train track. God, so must be a lot of pollen in the air today. Okay, the commercial value of the lightweight of the nickel iron alkaline battery is that less power is required to haul it, whether on railway passenger cars, where the savings appears at the locomotive drawbar, or in industrial trucks where more of the energy of the battery is made available for useful work. Okay, exercise 4. Physical characteristics. Heat dissipation. Compare the tray assembly of the nickel iron alkaline battery. See, that was a word string. But in this case, they added laboratory between alkaline and battery. That's exactly what is happening. I read by word strings, like what is likely to follow the next by historical construction of sentences and things like that. I think it's because I've sped read from an early age. It's just the way my apparatus is my visual, my eyes to my mind to my mouth. I think that's how it's wired. It's word strings, and these they've done things here to where you can't use that effectively. This sounds like a good excuse, right? Okay. Alright, compare the tray assembly of the nickel iron alkaline laboratory battery with that of a lead acid battery. If no specimen of the latter is available in the laboratory, a 3-cell automobile battery will serve. Note that in the alkaline battery assembly there are free spaces on all sides of the individual cells, while the lead acid battery assembly is solid. Okay, little note. Back in the day, automobile batteries were 6 volts. They're 12 volts now, but they were 6 volts back in the day. And each cell would be 2 volts. And so you put 2, 2, 2 together, you get 6 volts. 2 plus 2 plus 2 is 6 volts. So that's what they mean by that, if you didn't know. Note also that the alkaline cell containers are steel. Those of the acid cell hard rubber. I read that with the wrong inflection. Note also that the alkaline cell containers are steel. Those of the acid cell hard rubber. Look up and compare the coefficients of heat conductivity of the two materials. These comparisons serve to explain why surplus heat is more readily dissipated from the alkaline cell. This is important since all batteries generate heat both on charge and discharge, which must be removed rapidly enough to prevent overheating. Examples of its commercial importance are industrial truck batteries operating in warm weather, mine locomotive batteries in the high temperatures common underground, and railway passenger car lighting, and air conditioning batteries on which the load demands are usually heaviest and heat generation most rapid when the weather is warmest. Exercise 5. Chemical characteristics. Freedom from deterioration. The electrolyte of the nickel iron alkaline battery is a solution of caustic potash, P-O-T-S-H, potash, specific gravity 1200, which acts as a preservative of the steel containers, grids, and other parts of the cell. To demonstrate, immerse a specimen of polished steel in a caustic potash solution of the concentration used in the cell and preferably chemically pure. Leave overnight. In the morning, the steel will be found as bright as when first immersed, so it doesn't rust. Exercise 6. Electrical characteristics. Easy to lay up. Lay up means put away or mothball or decommission. Discharge a nickel-iron alkaline battery to 0.5 volt per cell or less at normal rate, or start with a battery already discharged to 0.5 volt per cell or less. Flush the cells if electrolyte is not already at correct level. Attach short circuiting connectors to groups of not more than 5 cells each. With this simple procedure completed, the battery may be laid up for any desired period of time in a clean, dry place without requiring attention of any kind. When it is to be put to use again, an overcharge at normal rate is the only preparation necessary. Yeah, it's like a time capsule. The commercial importance of the ability of the alkaline battery to stand idle indefinitely without attention or deterioration lies in the fact that industrial plants, mines, and railroads experience seasonal or other variations in business, so that part of the batteries in use when activity is highest often must be laid up at other times. With alkaline batteries, it is simple. With acid batteries, trickle or periodic charging is required to retard sulfation. Caution: do not try this exercise with a lead-acid battery. It would be injured, if not ruined. Exercise 7. Electrical characteristics. No finish rate limitations. Use a nickel-iron alkaline battery which is on charge. After it reaches a fully charged condition, continue the charge at normal rate for 1/2 hour. At the beginning, middle, and end of this interval, take voltage readings. All 3 readings will be the same if the cell is fully charged. Note that all cells are gassing freely. With charging current flowing at normal rate, all batteries will gas both when fully charged and as a charge condition is approached. In lead-acid batteries, gassing is harmful because it tends to dislodge the active materials from the grids. The need of preventing excessive gassing has given rise to the term finish rate, meaning a low rate to which the charging current should be reduced toward the finish. Gassing cannot harm the nickel-iron alkaline battery because of the use of steel pockets and tubes in which the active materials are secured. As a result, it is free from finish rate limitations. This reduces the total time required for charging without risk of injury and is of commercial importance whenever the available time is limited. So that means you can heavy duty fast charge them. If you run out of time, overcharge them, I guess. But that's not ideal. But it says it's possible. Exercise 8. Charging constant current method. As its name implies, this method of charging consists in passing of... I took a speaking college course, and I had it down pat, and that was a while ago. And use it or lose it. I get so occupied with other things, other obligations, that I don't usually publicly speak so much, and I'm running into a situation where I'm almost unable to continue. But we're gonna power through this. Okay. This is from the horse's mouth. Okay. This was not available in such an easy format last year or before on YouTube. Maybe even a week ago, or maybe even a day ago on YouTube. And certainly not free to the public to listen to. Now there's other videos and things you should watch, especially the old tour of the Edison factory video, how they make these, because this text goes into that later, but to actually see it is amazing. Okay, so This is why these are so long. I keep talking about other crap. Alright. Exercise 8. Charging. Constant current method. As its name implies, this method of charging consists in passing an appropriate... I just want to, like, have, like, a high-speed camera, like, on my eyes, on my mouth, and on the page, and, like, get the correlation of at what point am I unable to pronounce what is upon the page. That's highly interesting to me. But anyway, let's continue, or let's restart. As its name implies, this method of charging consists in passing an approximately constant current through the battery from start to finish. The several hours required to charge a battery that has previously been discharged to the extent of its rated capacity is perhaps too long for the usual laboratory exercise, but a period of a half hour in the course of a charge should be sufficient to demonstrate the method. Connect a discharged or partially discharged battery through a rheostat to a charging source and adjust the current to normal rate. After 15 minutes, take an ammeter reading. The rate should be found to have fallen below normal. Readjust rheostat to raise the current to normal. Repeat 15 minutes later. The same procedure followed from start to finish constitutes a so-called constant current charge. The current actually varies downward slightly between successive rheostat adjustments, hence is only approximately constant. This method of charging requires continual manual supervision and is gradually being superseded by automatic methods. Yeah. Exercise 9. Charging, constant potential method. This method of charging consists in use of a constant voltage charging source and results in a high current rate at the start, which gradually declines as the charge progresses and the counter voltage of the battery increases. To demonstrate the characteristics of the method without devoting the time required for a complete charge, connect a fully charged battery to a charging source having a potential of not less than 1.75 volts per cell and a current carrying capacity of not less than double the normal rate of the cells. Adjust rheostat to reduce the voltage at battery terminals to 1.70 volts per cell. Take an ammeter reading. By means of the rheostat, vary the potential at battery terminals up to 1.75 volts per cell and down to 1.65 volts per cell. Take ammeter readings and note the wide range in current rates. This demonstrates the principal shortcoming of the okay, let me explain something. When I went on YouTube trying to learn everything I could possibly learn about this technology, I kept running into videos that were super short, like a few minutes. And then I got aggravated. So I'm doing a long video. It's full of my inability to talk, but it is full of information. So I would say if you're able to have an attention span, you'll be able to make it through this. But I'm just saying, there are other videos on this technology, maybe other people, but this is going to be one of the longest ones out there. And for your time, you will learn things if you can filter through my amateur presentation skills. And it's probably going to be worth it, okay? But from my perspective, there's so many videos out there like 2 minutes, 6 minutes, whatever. I'm like, I want some more. I want some more knowledge, and it just wasn't there. It's like, what? So I'm trying to remedy that, okay? Whether people are going to appreciate it or not, and this is a very small slice of humanity that even wants to learn about this stuff, so I don't have a big expectation. But for the people that do, I hope I'm a valuable resource. I'm trying to be what I would want to be. I'm trying to be what I would want in a presentation. And this is some heavy info, so maybe me breaking it up by my mouth breaking down is actually quite welcome. Other people want to fast charge their brains, and it's awkward to have slow stuff, I guess. So, all right, I lost my spot. Okay, we're just gonna read it over again because I don't want to miss anything. And the way I talk, you've probably forgotten what I was saying anyway. Exercise 9, charging, constant potential method. This method of charging consists in use of a constant voltage charging source and results in a high current rate at the start, which gradually declines as the charge progresses and the counter voltage of the battery increases. To demonstrate the characteristics of the method without devoting the time required for a complete charge, connect a fully charged battery to a charging source having a potential of not less than 1.75 volts per cell and a current carrying capacity of not less than double the normal rate of the cells. Adjust rheostat to reduce the voltage at battery terminals to 1.7070 volts per cell. Take an ammeter reading. By means of the rheostat, vary the potential at battery terminals up to 1.75 volts per cell and down to 1.65 volts per cell. Take ammeter readings and note the wide range in current rates. This demonstrates the principal shortcoming of the constant potential method of charging. Small voltage fluctuations in the line produce such wide variations in current rates that batteries are likely to either overcharge or starve. Moreover, to charge a battery in 6 to 7 hours, a starting rate about twice normal would be required, which increases both demand charges and the necessary capacity of the charging equipment. No battery manufacturer recommends constant potential charging. Exercise 10. Charging method. Sorry. Let's get my twang back. Exercise 10. Charging modified constant potential method. By use of a somewhat higher voltage than in constant potential charging and the insertion of a series This is the pollen making my nose itch, or is it the text? Okay. Exercise 10. Charging. Modified constant potential method. By use of a somewhat higher voltage than in constant potential charging and the insertion of a series resistance between the charging source and the battery, this method ensures against excessive rate fluctuation, and by selection of proper values in potentials and resistances permits an average of normal rate without excessively higher rates at the start or unnecessarily low rates at the finish. To demonstrate its characteristics, connect a fully charged battery to a charging source having a potential of not less than 2.05 volts per cell through the following fixed resistances. So there's another table here. I'll present it. What this reminds me of? It reminds of docking the space station, or docking a space capsule to a space station, because they've got to maneuver things through a camera, and it gets closer and closer. I'm not gonna ask you if you're getting that, because that's an inane idea. Okay, let's cross our fingers on that. By means of a rheostat, reduce the potential across battery and fix resistance to 2.00 volts per cell. Take an ammeter reading. Now vary the potential up to 2.05 and down to 1.95 volts per cell, and from the ammeter read the current variations. This will demonstrate how the use of a series resistance cuts down variations in current rate with fluctuations in line voltage. Modified constant potential is the best and most extensively employed method of charging batteries in industrial, truck, mine, locomotive, and other services, which the duty involves full or approximately full cycles of charge and discharge. By using ampere hour meters interlocked with circuit breakers to terminate the charge, the system may be made fully automatic, thus eliminating the human element and ensuring uniform and dependable charging, long battery life, and economical operation. Recommended equipment for laboratory instruction and practical industrial storage battery operation. This is a list, I'll read to you. Portable laboratory batteries. Motor generator sets or rectifiers for charging. Voltmeters. Ammeters. Fixed resistances. Rheostats. Self-filling outfit. Ampere hour meters and circuit breakers. Series parallel switches. Copies of Edison Instruction Manual 850X will be supplied upon request. Here we go. Now we get to some fun stuff. Get out of the lab and into the factory. A trip through the factory. Taking a trip. Okay. This is gonna be full of pictures and less reading, so the reading is dissipating. Okay, I'm gonna read the captions and then the main text. Acres of steel are moved with ease daily by steel storage batteries in the great mills of the steel industry. Photographed by Johnson & Johnson. This giant tool of industry can swiftly handle a load of 30,000 pounds. It transfers coiled stock from one operation to the next, or from finish point to the carrier. This giant is careful as well as dexterous. It is powered by an Edison battery. The steel it is handling in the illustration might be on its way to the Edison storage battery plant in West Orange, New Jersey, for use in making more Edison steel storage batteries that will power other giants of industry. Try to move my hands so I get a better idea. So it's a early forklift type thing moving big old rolled steel. So hopefully you got a good image of that. Next page. Airplane view of plant at West Orange, New Jersey, where Edison nickel iron storage, where the nickel. Usually, if the words aren't configured right, it's because I missed a word. Airplane view of plant at West Orange, New Jersey, where the Edison nickel iron alkaline storage battery is made. And then down at the bottom, positive plate, positive tube, negative plate, negative pocket. So tubes and pockets are illustrated. That's good. I was wondering about that personally. it show and tell or oops, where's that on? Okay, there we go. We're straightening it out. The show and tell or tell and show. And down at the bottom, Section 4. Section 4. A trip through the factory. Production of the Edison nickel iron alkaline storage battery requires a chemical plant for the active material nickel and the active material iron, and a rolling mill and fabricating plant for the steel for the cell containers, grids, perforated steel tubes, and pockets within which the active materials are retained, and other structural parts of the cell, all of which are made of steel. These plants are unique both in the nature of the processes employed and in the degree of precision. Can I say precision precisely? These plants are unique both in the nature of the processes employed and in the degree of precision attained. Here are to be seen methods of fabricating steel which can be found nowhere else in the world. Electrochemically active materials are produced commercially to more rigid standards than those customarily designated as chemically pure. Quote, chemically pure, unquote. These processes have proven of such interest that a brief picture journey through these factories is presented on the following pages. So, Thomas Edison had such trouble sourcing high quality materials for his inventions that he decided to become his own supplier. And that's a very intelligent decision. Become your own supplier for all your manufacturing. You source the raw materials, and they go directly to your factories. There's no middleman, and there's no lack of information of what the status of material quantities are and such. You can run things more efficiently and controlled to your high standards. Okay. So again, I'll read the descriptors, and then I'll show the pictures, and I'll read the main text. Making active materials in nickel flake. Photographs in this section by Robert Yarnell Ritchie. Electrode positing nickel on copper. That's one word, electrode positing. I've never read that word in my life or seen it. Electrode positing. It must be like depositing, but with an electrode. Regulating thickness. That must be for the steel sheet. Stripping sheet from cylinder. Cutting into 1/16" strips. 1/16, so it's 1/16" strips. Then into 1/16" squares. Removing the copper. Taking a sample for a laboratory test. Padlocking the box. That's that nickel flake. This is terrible. This is gonna be so poor quality. Sorry. Okay. Maybe if I stand up. No, I can get it. Hold on. So that's the first images. Can't even see that one. So that nickel flake, where they're padlocking, apparently Edison would take a pinch of it and fling it in the air, and it would like slowly glitter and fall, but it was like magic pixie dust. It's probably why they're locking that so it doesn't open and wind gust hits it. Alright, or it's probably pretty valuable too. First step in production is making the active materials, iron and nickel, both believed to be the purest ever produced. Part of the iron produced is diverted for use as pharmaceutical iron. Nickel flake, used to ensure conductivity within the positive active material, is the lightest pure metal ever produced. The paper in this booklet is 85 times as thick. That's incredible. These are really thin pages, and if that's 85 times thicker, that is some thin stuff. It is produced by electrode position. Electrode position. It's another word. It's one word. There's no spaces. Electrode position. Its thickness accurately regulated by a sensitive ampere-second meter. After sheets containing 125 layers of nickel have been electrode posited, they are stripped off the cylinder, cut into 1/16 inch strips. How would you say that? 1/16 inch strips, then into 1/16 inch squares. Each of these tiny squares is then transferred into 125 squares of pure nickel by dissolving away the copper. The newly formed flakes are washed thoroughly, following which the water is forced out by centrifugal. The newly formed flakes are washed thoroughly, following which the water is forced out by centrifugal machines similar to sugar dryers. The flakes are next steam dried. The flakes are next steam dried, screened, and stored in boxes from which samples are withdrawn for laboratory analysis. Meantime, the boxes are padlocked so that by no possibility can the flakes enter production until the laboratory has completed its tests and has certified the quality of the batch as okay. Wow, okay, they tell us why. It's good. So next page. Construction starts with steel strip. Cold rolling. Slitting. Perforating. Grinding off burrs. Wire brushing. Nickeling. So these people that want to make these batteries again in their own garage and stuff, they don't realize how intense what they're getting into is. I think it'd be a better use of their time if they just find an old set and restore it, and really think about the economy of trying to make these by scratch. This is a really intensive process. Obviously. But yeah, I mean, there's people that are out there. They're like, oh, this is how it's done. Okay, I can do this at home. Maybe, but I've yet to see anybody that's made these precisely in the manufacture process that the Edison company did. There's usually like they've left out things or whatever, including the replica batteries from China. I mean, they don't have steel cases, and as shown, the plates are welded together instead of bolted together, so they're really hard to maintain and stuff, and just other little shortcuts and crap that don't compare favorably to the classic way of making these batteries. So anyway, all right, to the text. First steps in fabricating tubes and pockets. From stock, the strip. It seems like my mistakes are proportionally uh, coefficient to the length of the text. So if it's a long text, it takes a while to make a mistake, but if it's a short text, it doesn't take very long. It's highly interesting to me. Sorry, I have to say. From stock, the steel strip is cold reduced on the modern rolling mill shown, which holds which holds tolerances within 0.001 inch. It is then sheared into narrower strips. Next comes continuous perforation. Stock for the positive tubes receives 550 perforations per square inch. Stock for the negative pockets 1900. The perforating is performed continuously by circular die. That's for English as a second language people or whatever, third, fourth language. By circular die, that's D-I-E-S, dies. Die. It's not die as in the bug died. It's die. It said die, but it's D-I-E-S. The perforating is performed continuously by circular die, one of the few processes of its kind in the world. Burrs are then ground off by abrasive wheels, after which wire brushes give the strip a thorough cleaning. Now comes the nickeling, another continuous process. A given point in the strip passes through in 8 minutes. Okay. Now comes the annealing. Continuous tube forming process. Sawing tubes to length. Tube loading. Forcing steel caps in ends. Reinforcing with 8 seamless steel rings. Crimping ends. Part of me is like, just flash it and continue. But part of me is like, no, there's somebody there that wants to see every detail and doesn't want to buy the scan I'm going to try to do this. But they still need to see every detail, and they can't afford to buy a scan on my eBay shop. So I'm trying to do it. I'm trying to get it. It is going to be hard to scan this because, like I mentioned on my other video, the pictures go down in the spine of this book. They go way down. That's not easy way to. That's not something easy to scan. Plus the it's not a standard page size. Okay. Annealing the nickel perforated strip under hydrogen in furnaces such as the one illustrated above. welds the nickel so firmly to the steel that the strip may now be folded upon itself without separation. This is well illustrated by the automatic continuous tube forming process below, which twists the strip diagonally, turns the edges, and swedges the joints, producing perfect uniform tubes. Output of each machine is 20,000 tubes a day. After the tubes are formed, they are automatically sawed to correct length, then filled with 630 alternate layers of active material and nickel flake, tamped in with a pressure of 2,000 pounds per square inch. Then the metal caps are inserted in each end, following which each tube is reinforced with 8 seamless steel rings. Its ends are then closed in an automatic crimping machine. The tubes are now ready for insertion in the grid to produce the positive plates. Okay, to make the plates. Blanking the steel grids. Inserting the tubes. Meshing positive and negative plates. Fitting side insulators. Forming and welding the cell container. Forming the container. Side welding. Bottom welding. Inserting elements. Cover welding. This really breaks it down. He had all the patents and stuff, so he wasn't worried about showing the process, and it's quite interesting. Really. Of course, now it's still highly interesting, and I wonder how much of this could be the welding, at least, could be done by robots. The way, you know, they use them to put cars together. I'm trying to move this out. Okay. To make the plates. Now, don't get me wrong. If a guy is a pro at welding and that's all he wants to do, and that's the best way, let's do it that way. But so I'm just saying, these are very intensive, very labor. I already use the word intensive. These are very labor appropriating procedures. So bear this in mind if you get the wild idea that you're going to make these yourself. You probably use like a glass jar or something and whatever, but still, I mean, why are you reinventing the wheel? Find yourself an old set and rejuvenate it. At least be capable of that, and then you might be in the ballpark for making your own. To make the plates, steel grids are blanked out by a giant press and the tubes mounted, quote, rights, unquote, and, quote, lefts, unquote, alternating, then locked into place under a pressure of 40 tons. The plates are now assembled on pole pieces meshed with negative plates produced by similar automatic methods, and the plate group fitted with grid insulators ready for insertion in the cell container. The cell container, also made of nickeled steel, is first formed to shape the press shown, the side seam welded, and the bottom welded into position. By means of a special machine, the container is then tested in water under pressure to ensure that it is leak-proof. The elements are inserted together with pin insulators. That's PIN. The cover is then welded on, no need for internal repairs being ever expected. The cell is now ready for filling, forming, and assembly with other cells into batteries. Each step in the process is, of course, rigidly inspected. Filling with alkaline electrolyte is... We are almost done. I mean, there's just a few more snips left. Let's bear down and get through it. Filling with alkaline electrolyte, a preservative of steel, completes the cells. After forming, they are ready for assembly in trays into batteries for shipment. Almost going to be regret. I'm done. This is kind of growing on me. Determination of the carbon dioxide content is one of 86 tests regularly made on each batch of the electrolyte produced. That'd be interesting to get a hold of those test procedures. Examination of the nickel active material for physical size of the particles constitutes one of the 125 tests it must meet. Wow, see, they had quality control. Here, ferric acid, ferric F-E-R-R-I-C oxide. Here, ferric oxide, not acid. I don't know why I said that. Here, ferric oxide, which will later be active material iron, is being tested to determine when to take it from furnace. Samples of every batch of active materials produced are made into miniature test cells, which must produce a predetermined capacity at a predetermined voltage before being released for production. So that guy filling up the cells, he's just wearing goggles. That's a clue, because I got to make some electrolyte myself. I wonder if I could get away with just wearing goggles. Does he got... Oh, he has some thick clothing and some hand protection, too. But that's a clue. So this is almost like reverse engineering a little bit. Or at least understanding what's going on. I don't know how much this will actually help anybody, but it's highly interesting. It makes you aware of things you take for granted, that's for sure. Laboratory control of production. Nothing is left to chance in the manufacture of the Edison alkaline storage battery. After each step in making the active materials, samples must pass laboratory tests before going to the next process. Altogether, more than 50,000 separate laboratory tests are conducted in the course of a year solely to safeguard the quality and uniformity of the product. It might be supposed that this extreme care would guarantee correct functioning of the finished battery. Yet, as a final safeguard, samples of all active materials are produced. Samples of all active materials produced are made up into test cells, which must deliver the equivalent of full rated capacity before materials are used. It's the last page, brother and sister. Uses of Edison nickel-iron alkaline storage batteries. Alkaline batteries are employed as either normal or standby power source for operation of the following equipment. It's just a big list. I'll show you what I'm talking about. See? But I'll read it too. Here's my challenge. Can I read this without misstating anything? Here we go. Airway beacons, annunciators, ballistic testing instruments, call bells, car retarders, circuit breaker control systems, electric boats, electric motor trucks, electrocardiographs, electro-hydraulic steering controls, emergency lighting systems, engine stops, fire alarms, gas detecting devices, gyro compasses. Now a little bit of trivia. The V-2 German missile or rocket, it used a nickel iron battery to run the gyro compass. So that's highly interesting that they would put that in here in a 1940 book. Makes you wonder if they knew. Industrial trucks and tractors, isolated lighting plants, laboratory equipment, manhole lighting outfits, marine lighting and auxiliary power systems, meter testing and calibration, mine safety lamp. I messed up. Okay. Anyway, mine safety camp lamps and hand lamps. I messed it up again. Mine safety cap, like a cap, lamps and hand lamps. Mine signals. Did you really think I would get through this without screwing up? Multiple unit car controls, subways, and other electrified railroads. Portable electric sweepers. Portable spotlights. Soft lights. Portable spotlights. Railway car lighting and air conditioning systems. Railway interlocking plants. Railway interlocking plants. Oh, I read that already. Railway signals including subway and elevated lines. Seismographic instruments. Shot firing controls. Streetcar emergency lighting and controls. Telephones. Time clocks. Watchmen's lanterns. And then there's a gray page and then the end. So we got through it. Yeah. Okay. So I need to scan that at some point, but let me know if you're interested, because I'll tell you, this is gonna be like a very a video that isn't watched too much. Now you're like, okay, this dude, he seems enthusiastic, and but does he really have one of these batteries? I got several just hanging out right now. You don't think I don't? I feel like pulling one out to show you. Hold on. You got full of it, don't ya? That's okay. Sometimes I am. All right. So what we got here is about 3 volts of nickel iron battery. This was made for the Soviet Union, made in the Soviet Union. That white stuff is packing foam. Packing foam attached to cosmoline, which is like packing grease. But these are radio batteries. They haven't been ever activated. There's a date on there. You probably won't see that, but it's 183, so probably 1983. And it says Santra on there in English or whatever. But yeah, these haven't been activated yet. These aren't Edison made, but they're Edison technology used by the Soviet Union. And anyway, they come in this pack here. It's a rubber pack with a bakelite divider. Anyway, you wire your battery set up to this, and then you'd have power. And then it was portable, and it was light, and then gave you movement and communication abilities. And so as far as I know, they're unused. They were put away, war surplus, defense surplus, and like that. So it just goes to show that even if Edison uh, wasn't taken seriously after all that stuff was shut down in the 1970s, when Exide bought the manufacturing plant and shut them down, at least in 1983, the Soviet Union was still making, basic, using the technology. They were still running it. So they're out there. You can get a hold of some. Um, and then what I would do is study how to bring them back, because they're the one battery that outlasts the user, apparently. Something that can't be said of any other battery out there, including Tesla batteries. All that stuff wears out. Um, Elon Musk's batteries. So hopefully some really rich entrepreneur gets these back into production, because they do have some wonky characteristics, but overall they are quite a wonderful design, and almost non-toxic compared to lead acid and some other forms of batteries. So thank you for sticking with me. I'm going to try to put out some more videos before work and school requirements pull me away from my personal pursuits again. But please subscribe to my channel, and and the reason, or dislike. The reason why is that YouTube artificial intelligence views any interactions as a positive thing, and it raises your stats in its algorithm. So do me a favor and do that sort of deal. I always will have interesting videos. Sometimes not as frequent as I would prefer. It's because I'm tied down to some other commitments. But eventually, and others have done it too, they've become full-time YouTubers, and they're able to fund their projects, everything, straight off of YouTube. That would be a wonderful thing for me. So if you care about people, if you're not like a sociopath or a psychopath or something, which in that case I would understand, please go ahead and like or dislike the video, and maybe subscribe to my channel, etc. And this is like PBS. Oh, we need money. Oh yeah, send us some money. I'm not asking for you to send me money. Just do a couple click things. Let the algorithm take care of the rest. Alright, well, like I said, I plan to scan that in. I've got a bunch of other manuals and things like that I've been collecting, and I want to make them into a digital archive, which I'll sell on eBay for, I'm not saying like $50 trillion either, like $20 maybe, shipping included. And that would save you so much time doing your research, and let you determine whether these are worth your effort and whatnot. I've definitely spent more than $20 getting a hold of manuals, and more than several weeks' time trying to compile this information. If I could just pay $20 and get it, I'd be like, sign me up. That would have saved me so much. Yeah, so I'm gonna try that. It's probably not gonna work very well. Like I said, this is a rare technology nowadays, and people just don't have the wherewithal to pursue something like this. They just want something that works, and they'll just go with what's on the market. So at any rate, this is meant more, I guess, truthfully, this is meant more for people that want to get a hold of these types of batteries and get them back into service, especially in conjunction with solar panels and stuff like that, where your power charging is no longer going to cost you big bucks. I mean, it's coming as long as the sun gets its rays right into those panels, and those panels send the power to the batteries. you're in business. And so that's what it's meant for. It's more meant for the off-grid, I guess, or I guess whatever in whatever pursuit you want. Like I said, like even with the Soviets and their radio batteries, if you need like power to battery emergency radios and things like that, stuff that needs to work, and it's not gonna have a shelf life and whatever. It's something to think about. Um, me, technology does not have a political or religious ideology to it. Technology is science. All that it's beyond those human conceptions. So if I go over to some other country and they got technology uh, that I'm interested in, it's beyond the politics and human element. It's, does the tech work? Why why haven't I had this in my own country, or why isn't available and whatnot like that. So do me a favor, don't get all political or religio about, oh, he's got Soviet batteries. Look, I'm after nickel iron batteries, and if they were the only manufacturer at that time and they got war surplus and I came upon them and got them, and I need to get them going again, hey, that's life, man. And well, man, life is not perfect. Use what you can use, especially on a budget like I'm on a budget. You got to do what you got to do to get a hold of the tech, because you got limited time, limited funds. They got to be allocated to the most feasible uh, pursuits, and see it sometimes unfeasible because no one else is doing it. You're doing it to for your own personal satisfaction and interests and education and whatnot. So if it comes to the point where these are remanufactured, uh, and I'm talking with steel cases, pretty much to spec, pretty much like those Russian ones. Those are still nickel plated cases. Um, I'm gonna try to get one of these out of here, because this is a hard record, and we might as well see what they look like. They might have been glued down. What the? In that case, I don't want to. I have some that are loosey goose, and these aren't. So maybe they have been glued down. Tell you what, now hold on. Alright, we're back. Okay, here we go. Now I kind of look like that Dr. Lupo guy that made a video on these two. There you go. Steel case. It's painted with that alkaline resistant paint. Right? I noticed there was some manufacturing variance in these. Some of them have the terminals like closer together. This is one of them. You see what I'm talking about? So that's something to consider. But yeah, you would need a screwdriver to get in those. Some of these have another slit, so you can use the cross-shaped screwdriver or the flat screwdriver. So yeah. All right, so we know that these were made also, besides the United States, they were made in Europe, Russia, and China. So and the Chinese ones come in plastic cases. And I think they deviated from the intensive flake and bars and stuff like that. They have well, I know they have a different thing going on. So, and who knows what those Russian ones have in there? I'd have to take a little scope and go down a lighted little scope and go down inside and look around. I don't have that with me. So anyway, trying to make this video an hour 30 just like the other one, but it's getting close. So I've said my spiel. I also have other Edison batteries, some A4Hs. I want to get those going. What I plan to do is make some more videos. Hopefully during my time off. It's probably going to be the only time I have off all this year, maybe for the next couple years. The way I'm scheduled, it's crazy. I want to get some of that electrolyte mixed up and investigate the battery oil mystery. Supposedly it's just mineral oil. Like Edison would sell like colorized mineral oil. I want to get some pure mineral oil and put it in there, possibly. I've been cautioned not to. They supposedly can get up inside the components and run them, but I don't know. Especially batteries that aren't going to be moving around. And if it's just floating on the top, I mean. But, yeah. So, there's stuff there's stuff I'm investigating as well. So, I'm making these videos. I hope they serve to give you information. That's the point. Information should be available if one wants it, and they're not going to use it for destructive purposes. So hopefully this helps you out. Thank you for your attention span and for checking out one of my hobbies, one of my many hobbies, my all-consuming hobbies. Anyway, it's like my time off is like I work intensely on my time off. It's amazing. So, all right, well, stick around. Remember, subscribe and like if you're watching this on a YouTube platform, or come find me. I'm being more and more prevalent on the internet, and like that. So, okay. Well, we're not going to reach an hour 30 after all, but that's fine. I've said what I need to say. Time is precious. We don't want to be wasting it. Alright. Thank you very much. And let's see if we can... I'm still talking about stuff, trying to make it an hour 30. I mean, I admit it. Basically, what I'm trying to do is I want people to restore these batteries versus scrapping them. They're hard to make, obviously, and they can be utilized far into the future. Why would you destroy something that could provide you good service? I'm trying to get the word out. I want people to find these and restore them, and maybe even put videos up for their process and how they did it, because it's highly interesting. I mean, if I had, it's like the golden goose that's laying electric eggs. Serious. Why would you kill a goose? It's like the old fable. Why would you destroy the golden goose if it was putting out eggs for you? Why would you scrap it? No. Get your gooses back into goosing out the electric eggs. Right? Does it make sense? I hope. But anyway. This is almost like people who want to restore old Model T Fords, or they want to restore old airplanes, or they want to restore, I don't know, what's something people like to restore that's antique, wrought iron fences or something, you know. This is a video aimed at the Edison battery restoration community. Okay. And once again, I emphasize, before you decide to reinvent the wheel, or reinvent the Edison battery, in this case, please experiment on getting some old ones and seeing what the parameters are, and understanding what kind of huge effort you'll be doing to do that. I'm not saying that it's impossible, but I'm just saying it's not practical, at least for me. It might be for you. Maybe you got a lot of funding and the expertise and the materials and the ability to do it. But for the hobbyists, for people like me, I would highly suggest that you find these through Craigslist, through eBay, through word of mouth, through you know, industrial auctions, whatever, and get a hold of these and get them to where you want them before you decide to literally redo something that was already done. I mean, I'm saying it'd be more economically feasible if you're still in the economic paradigm, which I'm trying to escape myself, to get an old set and rejuvenate it and get it working. And it's supposed to outlast you anyway, so might be a thought to do it. Okay, we reached an hour and 30. Thank you very much.